Okay, welcome. Hopefully you had a good break. All right, we're going to continue on here. Again, we're off to chapter 6 and hopefully some 7 as well. Again, we have some labs coming up here in an hour or so hopefully we're ready to go on that. So in this chapter, we're going to talk about chemical reactions and sort of chemical equations, how to balance them. So let's get into that. So first off, how do we know sort of a reaction has occurred? Good talk. There you go. Sometimes we'll see a chemical change or a color change, actually. A solid is formed. That usually means some type of precipitate was made, like the reaction you're going to do today in lab. You're going to make a solid as you mix a couple of solutions together. Sometimes we will see bubbles that have formed. Usually, if you see some type of bubbles, that usually indicates that some type of gas has been formed. So remember that a chemical reaction is a chemical change, and that means that what you start with and what you end with are fundamentally different things. You have really created something new from what you started with. Also, sometimes we see things like heat or flame is produced or absorbed as a result of a chemical reaction. If you're, for example, holding a test tube and it feels hot to you, that would indicate that that reaction is exothermic, giving off all that energy to your hand, which is why your hand starts to feel hot. If you're holding a test tube, for example, and it starts to feel cold to you, then that would imply that perhaps that reaction is endothermic. It's sucking out all the heat and energy from your hand, which is why your hand ends up feeling sort of cold in that sense. Here again, we can see some bubbles being formed there. Also, some color change is sometimes an indication that a chemical reaction is taking place. And that's pretty much what you'll be doing just a bit there, making a yellow solid along the way. And again, bubbles usually, again, indicating gas. A combustion reaction, for example, when you light the Bunsen burner and you get the flame that occurs, obviously some more bubbles there. So one way that we represent a chemical change is through a chemical reaction. And a chemical equation is what is used to represent that. And really, a chemical equation is the formulas for everybody that is reacting. It's also the formulas for everybody that is being made. So, for example, here we can take hydrogen gas, which is sometimes referred to as molecular hydrogen, reacts with oxygen gas, which is also molecular oxygen, is sometimes referred to, and forms water in this particular case. So water here is what is formed as a result of this reaction. Now, when we look at this, we could say, as I mentioned there, sort of in words, and it's really important that if you are given things in words and you do need to turn them into sort of a chemical equation, it's really important that you actually sort of get all the correct formulas down first. And that's something that sometimes people mess up on. We're going to talk about balancing here in just a second, but sometimes people mess up on the idea of they want to kind of balance and write the formulas at the same time. And usually what ends up happening is you end up with the wrong formulas, things will not balance. So you always want to kind of go in that order. If you have things in words, you shouldn't worry about sort of the equation and balancing it. You should just make sure you get all the proper formulas down. One of very common mistakes that people make, again, is something like these two: hydrogen gas, oxygen gas. They just write H and O. And again, remember, those are our diatomic molecules, so they do come as H2 and O2 naturally. And again, that's a very common sort of error that people make. Now, when we look at this equation, there is something wrong with it, and that is what is known as it is not balanced. And this is sometimes referred to as the unbalanced equation. It is not balanced because if we look at it, we could just add up everybody here. We have two hydrogens over here. We got two hydrogens over here. Remember, the number goes to the guy to the left. We have two oxygens here, but here we only have one oxygen. And that is a problem because the law of conservation of mass tells us that we don't create nor destroy anything along the way. So we should have conservation really of our elements. And that's because in a chemical reaction, the only thing that happens is we are breaking bonds and making bonds, and that's all electrons. And because we don't do anything with what's in the nucleus, we don't touch the protons, we don't change the elements. So we never change the elements in a chemical reaction. So that means, again, if we started with 4 carbons, you should end with 4 carbons. They should be in different things, perhaps on the other side of the arrow in most cases, but we shouldn't lose anything along the way. So in this particular case, we do want to fix it, and we can fix it by balancing the equation. And in this particular case, since we have basically 2 oxygen on the left and only 1 on the right, we can actually balance it by putting a 2 here, and that is a coefficient. As we'll talk about, that is the only way to balance the equation. You should only change the coefficients. You should never change the subscripts, because if I change the little numbers there, then I am changing what that compound is. It would no longer be water, obviously, if I got rid of the 2. So we don't want to change anything other than put numbers in front. By the way, when we do put numbers in front, it does count for everybody behind it. So that would give me, for example, here 4 hydrogens now and 2 oxygens. So if we do put a number in front, it goes to everybody behind. That's okay in a sense, but you have 2 oxygens. We did fix the oxygens, but the hydrogen now is unbalanced on the other side, and that also can be fixed by putting a coefficient of a 2 in front of it. And again, that goes to the guy behind it as well, and that would give me 4 hydrogens. So now what we have is a balanced chemical equation by putting those coefficients in front. And that is always what you want to do. And as we'll talk about, that's pretty much what happens when you go to balance an equation. You'll fix something and then frankly screw something else up. So you got to go fix that. Eventually, everything should fall into place. And you should always, always, always make sure that your equation is balanced. Pretty much, there's no time in chemistry that you have a chemical equation usually and you're using it that it should not be balanced. So you should always make sure that is balanced. I would say that if you do see coefficients, it's probably balanced. You should still take a check of it. But if you definitely don't see any numbers in there in front and coefficients, you should probably take a pretty good look at it. So this balanced equation does have a couple of parts to it, and on the left-hand side of the arrow, those are what are referred to as our reactants. So these are our reactants. That's our starting material in a chemical reaction. On the right-hand side of the arrow, that is our products, and that is what is formed as a result of a chemical reaction. So reactants on the left-hand side, products on the right-hand side. Other things that you commonly will see in equations are states, and you will see the states sometimes written next to the formulas, and that's S for solid, L for liquid, G for gas, and AQ are different sort of states that you have. And again, that's solid, liquid, gas, and AQ is aqueous. It's basically a water environment. It's a solution, a homogeneous mixture, basically. And those are very common things that you'll see next to the actual formulas. Other things that you'll sometimes see, like on top of the arrow, for example, you may see a delta symbol. And usually if it's on top of the arrow, that usually means heat. You'll sometimes see maybe something like water on top of the arrow, which means you dissolve something in water. And a lot of times, though, up on top of the arrow, you will see a catalyst written. And that could be something like a metal, like platinum. It could be something like H plus, which is an acid. And catalysts are not reactants. They're not products. And as we talked about, I think in the energy chapter, they do not get used up. They're usually just there to speed up the reaction. So basically what a catalyst does, as I think we did talk about a little bit in the energy chapter, it finds really an alternative pathway for that reaction to occur, a more efficient pathway. the end result is usually it will speed up a chemical reaction. So sometimes you'll see things written on top of that arrow, and again, they can be a catalyst, and really they're just there to facilitate that reaction sort of happening more efficiently. Yes, sir. Say again? It's a good question. There is a difference between liquid and aqueous. So, for example, water by itself is a liquid. Yeah. So that's a pure liquid by itself. If you took water, which is a pure liquid, and then you added, say, some solid sodium chloride, some salt to it, right? The salt will dissolve in the water and you will make a sodium chloride solution, which is aqueous. So aqueous is usually a solution which is a homogeneous mixture. So it's usually something dissolved in something else. A solution has two parts. It's a solute and a solvent. In this case, the solvent's the larger part, which is the water, and the solute is, in this case, the sodium chloride. So it's really a mixture, a homogeneous mixture, and it's usually something dissolved in something like water. It doesn't always have to be water, but a lot of times it is water. Yeah. Other questions? But a pure liquid is just one substance by itself, nothing else kind of mixed in with it. Question. All right, so here are some interpretations of chemical reactions which we'll use later on when we do some calculations, and we'll kind of revisit that. But you can look at those coefficients as some relationships. We could say that two molecules of H2 react with one molecule of O2 to give us two molecules of H2O, and that again is just the coefficients. This is the relationship we'll use when we talk about stoichiometry, which is a mole to mole relationship. Also, just from the coefficients in the balance equation, 2 moles of hydrogen gives us 1 mole of oxygen and 2 moles of H2O. So as I mentioned before there, we have states which are commonly found in chemical reactions. So you can see there, these guys are in the gas state. Then we have some solid, gas, and liquid sort of happening. We also sometimes will use equations to represent physical processes that are occurring, sort of physical changes. And that's what we see here. That is liquid water going to ice, basically. So that is a physical change. But we also sometimes will use an equation to represent that. Again, the only difference here is the actual state. Here is liquid water going to gas, which is steam, and that's the process of evaporation, which is also a physical process. And again, we sometimes will use chemical reactions or equations to represent both chemical changes and also physical changes that are occurring as well. And as I mentioned earlier there, sometimes you'll see some things written on the arrow, and this, for example, is a formation of a solution which is aqueous. And again, here we're basically dissolving that solid in water, and sometimes that's put up there up on top of the arrow. You'll sometimes see that. All right, so let's talk about the steps to balancing equations. And there's a few different methods you could sort of follow, but here's one sort of process, and we'll just kind of get into it in a second here. But you do want to make sure that you identify all the reactants and products, and especially, as I mentioned earlier, that if you're given everything in words, you want to make sure that you get down first off just the proper formula. So again, if you don't have the proper formulas down, like you're doing nomenclature, then you're going to have a really tough time balancing it. It probably won't balance for you because you're not starting with the right formulas. And again, that is always the order, as I mentioned, correct formulas, then balancing. Especially problematic for people is when they have to maybe predict what's on the right-hand side of the arrow, and all they have is what's on the left-hand side of the arrow. Sometimes people try to do the balancing and formulas together, so don't ever do that. Formulas first, then balance. Once you have that, you want to begin by balancing with the most complicated molecule. You want to use coefficients. Once again, only the numbers in front should change. And lastly, you want to make sure that you actually have balanced your equation. You want to make sure you have the same number of elements on each side. When you are done balancing the equation, and to do it properly, there's really two things you have to make sure of. All the coefficients need to be whole numbers. and they need to be the simplest set of whole numbers. So what do I mean by that? Let's just say, for example, you had an equation and this was an equation and you balance the equation with these coefficients here, 2, 4, and 6. Now, although it may be balanced with those coefficients, if you look at each of those coefficients, you could also go back through that and divide everybody by 2 and reduce everybody down by 2. And you should do that because if you could do that and still get whole numbers, that would give you your properly balanced equation that looks something like this. So sometimes what happens is sometimes people can see larger numbers and it will definitely still be balance the equation. But if you could go through all the coefficients and still reduce them down and still hit whole numbers, that is what you should do to have a properly balanced equation. Any questions on that there? Here's another approach. We're going to talk about a couple approaches here in just a second here. All right, let's just do one here together and sort of show you. Let me just show you how I would approach it here. So I would take this equation, and first off, I'm a pretty big fan of tables, and sometimes making tables as you're balancing an equation is really helpful. It kind of organizes things for you and sort of gives you an idea of maybe where you want to start. So we know there's a reactant side, which is on the left. We have a product side. And then frankly, you could just list all the elements involved here. So we have nitrogen, oxygen, and hydrogen. On the left-hand side, we have 1 nitrogen. On the right-hand side, we have 2. Left-hand side, I got 1 oxygen there. Right-hand side, I got 1 oxygen there. Left-hand side, I have 2 hydrogens there. Again, the subscripts count. And on the right-hand side, I have 2 hydrogens there. So starting out with here, in this case, I could clearly see from my table, everybody's balanced except for the nitrogens. So that seems like a really good place to start. So I could fix the nitrogen by simply, once again, just putting a coefficient. And here I will put a 2 over here on the left-hand side to balance it. Once again, that 2 goes to everybody behind it. And that would then give me 2 nitrogens. Now for my oxygen, I have 2 times 1, which is 2. And for my hydrogen, I still have 2. So again, very common. We fix one thing, kind of mess something else up. So now we fixed the nitrogen, but we did mess up the oxygen. And that's not a problem because I could easily see I could go to the right-hand side and fix the oxygen by putting a 2 over here as well. That again goes to everybody behind it. And that would then give me 2 nitrogens. 2 times 1 is 2 oxygens, and now 2 times 2 for the hydrogen is 4. So I'm almost there. I've now got the nitrogen and oxygen balance. I could clearly see from my table the only thing that's not balanced is the hydrogen, which we could simply fix by coming back to the left-hand side and putting a 2 there, giving me 2 nitrogens, 2 oxygens, and once again, 2 times 2 there is 4 hydrogens, and we would have a balanced equation. Again, making a little table, it oftentimes, like I said, sort of organizes things and it makes kind of maybe just where you should start pretty easy. I personally go with what seems to be the easiest to fix based off the table and just start there and kind of work my way around. A lot of times where you want to start, in my opinion, is where what looks easy to balance, and that's in only like one thing on each side. So it's not in multiple things. That element's only in one sort of formula on each side. Any questions on that there? Yeah. Yeah, there is, and we're going to see an example a little bit later on where maybe that would probably apply a little bit better. But for these ones here, where there's not too many complicated things going on, and by complicated things, usually what they're talking about is some more like polyatomic ions and stuff like that. So there's a lot going on with those. But here, you could probably, I would start with what seems the easiest sort of balance. And again, what you're looking for is Like, is it just in one thing on each side? And that's a really helpful place to kind of start. All right, so why don't you give this a go? Why don't you balance up this equation and see what you come up with? Okay, so let's take a look. Again, we're going to make a little table here. Reactant product side, we got carbon, hydrogen, and oxygen. So when we're counting up, we got 3 carbons on the left, 1 on the right. We got 8 hydrogens on the left and 2 on the right. We got 2 oxygens on the left. Here, though, for the oxygen, we do have 2 here, but we don't want to forget about that one, which is 1 more, and that is 3 oxygens in this case. So once again, in this case, I'm just going to look for what looks pretty simple. So carbon to me looks like a pretty simple thing I could start with to balance it. And to do that, I'm going to put a 3 in front of it. And once again, that 3 does go to everybody behind it. So that will give me 3 carbons. I still have 2 hydrogens. Now in terms of oxygen, I have 3 times 2, which is 6. And I still got that 1 over here, which makes it 7 in this case. Now, what looks easiest to me in this case is hydrogen to fix. The reason I perhaps do not want to start with oxygen is I see oxygen in this guy and this guy, a couple things on the right, and only one place on the left. So it's in a lot more places. So it's a little bit more complicated. In this case, I would leave that to the end. That's why I will tackle hydrogen, because when I look at hydrogen, it's just in one place on each side. So that's a much easier thing to tackle. So here to tackle the hydrogen, we're going to go with a 4 in front. Once again, that is going to go to everybody behind it as well. So that gives me 3 carbons. 4 times 2 is 8 hydrogens. Now for the oxygen, I still got the 6 for the front one, but now 4 times 1 is 4. So 6 and 4 is actually 10 at this point. Now saving that oxygen for the end, it's very easy to fix the oxygen. I could just go to the right hand or left hand side there and put a 5 in front of it. And now we got 3 carbons, 8, and 5 times 2 is 10. So this is what I was talking about earlier. Sometimes you'll come across a situation like that where you have a choice between maybe 2 elements where you should go next. I would go with the one where it's only in one thing on each side. Again, if you have something with multiple things on one side, like the oxygen here, probably save that to the end and things will sort of fall into place a lot better, kind of keeping and waiting for those guys till the end. Any questions on that one there? All right, continuing on here. Write the balanced equation for this one. Diboron trioxide reacts with water to form boric acid. So go for it and balance it up. Okay, so let's take a look. So once again, in this case, we have everything in words. So as I mentioned before, you definitely want to make sure you're starting with the right formulas first. So diboron trioxide, I see some prefixes, it tells me it's type 3. So di is 2 and tri is 3. So we get a little bit of that happening there. And that's going to react with water, which is H2O. 2,4 means we put an arrow, and we got some boric acid there. All right, so now we have all the proper formulas. Again, I wasn't worried about any type of balancing at this point. Now I'm going to worry about the balancing. So we'll make our table here, reactant product. Got a little BOH happening. And in this particular case, on the left-hand side, 2 borons, right-hand side, 1. Left-hand side, I got 3 oxygens there, and 1 more over here makes 4. Now for this guy on the right-hand side, this 3 does get distributed to everybody inside the parentheses. So I have 3 oxygens there. On the left-hand side, 2 hydrogens, and once again, distributing that 3 in gives me 3 hydrogens in this case. So again, if you got parentheses and a little number, you do have to distribute everybody in terms of that number. Now, again, in this case, not a lot to work with. So to me, I think boron seems like the best place to start. And you can probably imagine if you put a 2 there, that will take care of our boron. This 2, by the way, does go to everybody behind it, including the ones in the parentheses as well. So this gives me now 2 borons. I got, however you want to do it, 3 times 1 for the oxygen times 2 on the outside is 6. And same thing for the hydrogen, 3 times 1 times 2 on the outside, which gives me 6. So you do have to kind of distribute in and then kind of multiply out as well. Clearly, at this point, I fixed the boron, but messed up everything else. So the next place I want to look at is what again looks perhaps the easiest one for me to fix. And hopefully you would agree with me that hydrogen seems like a better move. I got oxygen in multiple places over here, and clearly I don't want to come back here and change anything on this side. So I only got one hydrogen on the left there, and I could fix that by putting a 3 there. Once again, that's going to go to everybody behind, which gives me 2 borons. I have 3 oxygens here, and then 3 times 1 is 3 there, which is 6. And our 3 times 2 is 6. So again, by actually tackling the hydrogen first here, it fixed the oxygen, and that's also very common. Sometimes everything will should fall into place at some point, even maybe without having to put another coefficient somewhere else. Any questions on that one there? All right, so why don't you do this one here, balance it up, see what you come up with. Okay, so let's take a look and see. So here we will make a table, perhaps. So reactant products, we got nitrogen, hydrogen, and oxygen. Left-hand side, 1 nitrogen. Right-hand side, 1 nitrogen. Left-hand side, 3 hydrogens. Right-hand side, 2 hydrogens. Left-hand side, 2 oxygens. Right-hand side, 1 oxygen there and 1 oxygen there. Gives us 2. So actually everything looks balanced except for hydrogen, so that's a good place to start. In this particular case, we actually need to put a number on both sides to get hydrogen balance. If you're not sure what number you're looking for, you take 3 times 2, that's 6. So that's like a common number there to get everybody to 6. So to get my hydrogen on the left here to 6, I need a 2. To get it to 6 on the right, I need a 3 in this case. And again, those numbers go to everybody behind it, which means we're going to distribute that. So we have 2 nitrogens. Hydrogen, we have 3 times 2, which is 6. Oxygen, we still have the 2 over here. Right-hand side, we have 1 nitrogen. We have 3 times 2, which is 6. And again, we're going to distribute that. So we have 1 oxygen here and actually 3 oxygens there. And that's going to give us 4 oxygens in this case. Once again here, I'm going to actually go with the nitrogen next, as we can see oxygens in multiple places. So I'm going to save that to the end. And I can fix the nitrogen pretty easily by putting a 2 in front of it. And by doing so, that gives me 2 nitrogens. Once again, going to distribute, that's going to give me now 2 oxygens there and 3. That gives me now 5 along with my 6 there. So everything is fixed here except for our oxygen. And obviously we only have one place to go, which is here. And we do have 2 oxygens. So basically we need to make our 2 into a 5. We obviously do not want to go back and kind of mess around with any of the coefficients at this point. And one way that you could do that is you could actually use a fraction and do something like 5 divided by 2. And if I do that, I will now have 2 nitrogens, 6 hydrogens, and when I take 5 over 2 times 2, the 2's cancel and give me 5 in this case. And it is actually balanced at this point. Yeah. That is exactly the right answer there. That's the question I was just going to ask. Can I leave it like that, though? And the answer is no, right? Because we cannot leave it as a fraction. It does need to be a whole number. But you could absolutely, like I just did there, use a fraction to balance the equation, but you cannot leave it in a fraction form. So we do have to actually do one more step at this point, which is get rid of the fraction. So although we could use the fraction to balance, we do need to get rid of it, and we need to multiply by the denominator. And by the way, we need to multiply everybody by that denominator, not just a fraction. So if I do that, that's going to give me 4NH3. That's going to give me 5O2. That's going to give me 4NO. And that's going to give me 6H2O. And if I didn't do anything wrong there, we should still be balanced. So let's see, I got 4 nitrogens on the left. I got 4 on the right. I got 4 times 3, which is 12 hydrogens on the left. 6 times 2 is 12 on the right. I have 5 times 2 is 10 oxygens on the left. I have 4 oxygens there and 6 there. Gives me 10, so it is balanced. So you could absolutely, like I just did there, use a fraction to balance the equation, but you do need to get rid of it at the end by multiplying by the denominator to clear the fraction. You cannot leave it as a fraction or obviously a decimal or anything like that. It does need to be a whole number. Any questions on that? Now, sometimes people are like, what fraction should I choose? It's a really simple formula to basically choose the correct fraction. So we were going to go in front of O2, and if you remember, what we were looking for was we kind of needed 5, right, in this example. So because we needed 5, that should always be the number on top, the number you need. So always up on top should be the number you need to balance it. The bottom number should always match the subscript. So it should always match the subscript, and that will always get you the right fraction. So number you need up on top, bottom guy should match that subscript. Any questions on that one there? So again, the properly balanced equation would be the one with all whole numbers at the end. All right. So let's talk about a couple other things that occur with equations. So try to think of one here. Let's do let's just say we have something like this, and to answer sort of an earlier question, this is what I would call complicated. Yeah, it says there is a lot of polyatomic ions in this equation, right? So in this particular case, when we look at it, there's actually 2 polyatomic ions on each side. And those, again, are a little bit more complicated stuff. If you have a situation like this where you have multiple sort of polyatomic ions on each side, I would not kind of go with the table method there where you kind of do it element by element. You absolutely can still do that. The problem is going element by element in this situation is there's a lot of like multiplying in, multiplying in parentheses. So there's probably a good chance you might screw up along the way. So in this case, because it's really complicated, I would actually keep the polyatomic ions together and sort of balance them as whole units rather than sort of separate ones. So what do I mean by that? I mean, like, for example, here, if I look at this, I basically have 2 NO3s on this side, and I have 1 NO3 on this side. I basically have 1 phosphate on the left, and I basically have 2 phosphate units on the right. So you could really start with either sort of polyatomic ion. One might work better than the other, and one might not work so well. Then you could just go back and start with the other one. So for example, let's just say I wanted to start with, say, the phosphate. So on the left-hand side, I got 1 phosphate. On the right-hand side, I got 2. I could fix that really easy by just putting a 2 in front of the phosphate on the left. That's going to give me 2 phosphates, which is what I need. And in this method, when you do something like this, the next place you should go is whatever it's attached to. So in this case, I also affected the sodium, right? And now for the sodium, I have 6, and that's where I should go to the other side and go to sodium and fix sodium with a 6. And when I do that, that fixes the sodium, but that now gives me how many nitrates? It gives me 6 nitrate units, which is where I should go next. And to get to my 6 nitrate units here, I will need a 3. That gives me 6 nitrate units, and now I have 3 magnesiums, which is actually what I need. So actually keeping those polyatomic ion units together and balancing them as whole units is really a good way to do that. Now look, if you chose wrong in a sense, so if I redid this guy here and maybe I don't want to say I chose wrong, but I chose the other polyatomic ion. Will it work as good? Maybe not. but let's take a look and see what happens here. So let's just say I started with the nitrate and I go, okay, I got two here and one here. So I'm going to put a two, right? And that gives me two nitrates and two sodiums. But when I come over here, that's not so great, right? Because that's not going to work. So I need, actually, I can figure it out from there. 3 times 2 is 6. So I know actually I will need that guy a 6 and that guy a 2, and I could actually pick up from that point, or I could just default and start with the other guy and kind of work it out that way. So sometimes it will work better with one versus the other, but you could actually fix it midway like I just did there and figured out, okay, obviously a 2 and a 3 is not going to work, but 2 times 3 is 6, and I can now get that guy to 6 and kind of fix it, and obviously finish up the rest of it by putting our 3 there as well. Or you could just go back and start with the other polyatomic ion and everything will fall into place. So however we want to do that. Any questions on that? You could absolutely still do it, like I said, element by element, but you're going to have a lot of multiplying in and multiplying out. So again, probably a greater chance that maybe something might not go so right. Why don't you try some here, and let me add one more. Bless you. How much about it? So why don't you give these guys a go, see what you come up with. So once again, here on the top one, I do see at least one polyatomic ion there, and that's probably where I'm going to start. On the left-hand side, I have 3 sulfates, basically. And on the right-hand side, I have 1 sulfate. So I could easily fix that by putting a 3 in front of my sulfate. That gives me 3 sulfates. Once again, in this method, where I want to go next is pretty much whatever that's attached to. So that gives me 3 calciums. So I'm then going to go to my calcium, put my 3 there. That gives me 3 calciums. That also now gives me 6 chlorides. That is where I want to go next. 6 chlorides gives me 2 irons, which again is what I need. And now I'm balanced again. A lot quicker probably than going element by element in this case. Um, and again, just kind of keeping those polyatomic ions together because they're really complicated is a good way to do that. Question on that one there. Yeah. Yeah, I would. I mean, if you're going to do this method where you kind of keep them together, you should just look at them as like units, basically. Like I have 3 SO4 units or 1 SO4 unit type of thing. Yeah. Other questions? All right, looking at the next one here, we do have a couple different polyatomic ions. We got nitrate, we got phosphate. And I would say in this case, you could start with either one. One might work better than the other. Perhaps a good approach is to start with the one with the higher negative charge or so, and that would be the phosphate. So that is where I'm going to start with. And here I have 1 phosphate on this side. I got 2 phosphates on this side. So to fix that, I'm going to put a 2 here. That gives me my 2 phosphates. Again, that's going to tell me now I need to go look at copper there, which is 6. I'm going to put my 6 here. That then tells me I need to look at my nitrate, which also is going to be 6 nitrates. I have only 2 nitrates on this side. So to get me to 6 would be 3. Then I look at the barium and now we're good. And that's usually what will happen is at some point everything else will just sort of fall into place and be correct. Any questions on that there? So again, that's probably a much easier approach with these really complicated sort of polyatomic ions. Obviously, if you don't have an equation with polyatomic ions in it, I would recommend just doing the table element by element like we did previously. That's probably your better approach. But if you definitely have these polyatomic ions, then kind of keeping them together is a good way. Any questions on either of those there? All right, take a look at the last one, and that was C4H10 plus O2, CO2 plus some water. So again, no polyatomic ion here, so I'm going to go back to my table approach which is a good way. Carbon, hydrogen, oxygen. So I got 4 carbons on the left, 1 on the right. I got 10 hydrogens on the left, 2 on the right. I got 2 oxygens on the left, and once again, 2 there and 1 more there gives me 3. So once again, going with the easier approach here as to what seems simple to balance. Carbon looks pretty simple to balance, so I'm going to put a 4 in front of it. That again goes to everybody behind it, which means I have 4 carbons. I still have 2 hydrogens. That's going to give me 8 oxygens plus 1 more here is going to give me 9. Once again, at this point, I have a choice between hydrogen and oxygen, and hopefully you chose hydrogen as it's only in one thing on each side, a lot less complicated in this case, and we can easily fix the hydrogen by putting a 5 in front of it. And to do so, that's going to give me now 4 carbons. 5 times 2 is 10 hydrogens. Now, in terms of oxygen, we still have 8 here, but now we have 5 times 1, which is 5, I believe. And so that is a lot of math there, but that's 13, I think, total there, if I am not mistaken. At this point, we again have a situation where we really want to come over here and we want to put our 2 basically into a 13. This is definitely a fraction situation. Once again, to do the fraction, up on top is the number we need, which is 13 in this case. On the bottom is the number that matches here, which is 2. And that gives me my proper fraction that I want. That's going to now give me 4 carbons, 10 hydrogens. And once again, when I take 13 over 2 times 2, they cancel and gets me 13. Once again, as we talked about, we cannot leave it like this, so we're going to multiply everybody by the denominator in this case to get rid of the fraction, giving me 2C4H10 plus 13O2. If I can multiply right, 8CO2 plus 10H2O. And once again, we should still be balanced. I got 8 carbons on the left and I got 8 on the right. Hydrogen, I got 20 on the left and 20 on the right. Oxygen on the left there, I got 13 times 2, which is 26. On the right, I got 16 there and 10 more there, 26. Yeah, so it is balanced in this case, yeah. Previous chapter there, we talked about balancing equations. In this chapter, we're going to talk about different types of equations and ways to classify reactions. A lot of reactions happen in aqueous solutions. Aqueous, as we just talked about, is a water environment. It is really a mixture, basically. So as was an earlier question, when we talk about something that's a liquid, like water is a pure liquid, and we add it to something, say like a solid, like our sodium chloride, again, that sodium chloride is going to dissolve and give us a sodium chloride solution, which is, again, aqueous. And again, that is the distinction. Something that's a liquid is basically one substance by itself, not really combined with anybody else. So our aqueous solution is, again, has really 2 parts. It's the solute and the solvent. And the solute is the smaller part of the solution. The solvent is the larger part of the solution. So when we look at that example I just did, which is our water plus our sodium chloride, this is our solvent. It is the larger part. And this is our solute, which is the part that's dissolved in it. And that does give us our sodium chloride solution. How do you know what is the solute in a solution? It's pretty simple. It is the name of the solution. So if you have a sodium chloride solution, sodium chloride is your solute, and probably water is your solvent, as water is a good solvent for ionic compounds. So if it's ionic compound, water is usually the solvent. Water does not always have to be the solvent. It's actually a pretty bad solvent for something that is molecular and not ionic. But in a lot of cases, if it is ionic, then water definitely will be your solvent in most cases. All right, actually, we should lay it up. We gotta go to lab. So we'll lay it up.